Hi guys, I'm just going to recap Shear and post a video for that. Please read through chapter 7 of your textbook. It'll give you a breakdown on where these formula come from that we're going to have a look at right now. And it'll give you an insight into where this shear comes from. So I'm going to run through this very carefully. We have run through this in class, but I'm just going to repeat it before I carry on with the other videos. Okay, the reference to the principal tensile stress, which we discussed in class, basically it's the resultant of all the stresses that cause this shear. If you look at our typical beam that we have over here, we need to design for two different states of shear in a pre-stressed beam. We have the state where it's uncracked in flexure and a state where it's cracked in flexure. Uncracked in flexure, we have the diagonal cracks as you would see in the web. Principal tensile stress is obviously perpendicular to that, and that's why we're getting our cracks there. Where we have a flexural shear, the principal tensile stresses are more parallel to the soffit of the beam, giving you these more vertical shear cracks here, and more likely to happen, the cracked inflection, in other words VCR, more likely to happen at midspan. VCO, uncracked inflection, more likely to happen at the end of the beam. I'm going to continue now and just work through just basically how to apply those two formula. As I said, the textbook gives you an insight as to where the formula comes from, how it's derived. Bear in mind that we also have, of course, just like normal reinforced concrete, we have that we check shear in the ultimate limit state. It's one of the conditions in which pre-stressing is checked in the ultimate limit state. And that there is a maximum shear stress limit, and it's limited to the lesser of 0.75 times root FCU or 4.75 MPa. Okay, so we just need to bear that in mind. Okay, uncracked in flexure. This is more than likely going to happen at the end of the beam. Like I said, where shear is higher and where the bending is lesser. This formula that we look at, please refer to your textbook for the makeup of the formula. B is the width of the web. When I say the width of the web, I mean if it's an I-beam, for instance, it's the narrow width of the web. It's not the width of the flange. Okay, so don't refer to the width of the flange, it's the width of the web. H is the overall depth of the section from top to bottom. Don't confuse that with the depth from the steel to the compression face. Okay, FCP, something that we need to calculate here. This is the compressive stress at the centroid of the section due to the pre-stress only, and it's always taken as positive. Okay, so basically this is your P upon A, PE upon Z, only that part. But we'll go through that in the example. And then FT over here, 0.23 times the root FCU, also always taken as positive. We'll go through that with the example in a minute. Now, another thing to take into account here, the shape of the pre-stress tendon, the incline shape of the tendon is going to actually help you with the shear stress capacity of your beam towards the end. And we can take that vertical component and we can add it to this. So we'll work through that as well in the example, and I'll show you how to calculate that. Right, now before we get too far gone, I just want to go through the example. I'm just going to pause now. Okay, I've just jumped ahead now to our typical example that we were using in losses. So we're just carrying on with that example basically for shear. All of this will be familiar if you look back to lecture 3 where we calculated our losses. What we've done here is we've done a shear force diagram just for one half of the beam. Now this example here, we wanted to find the VCO and VCR 3 meters from the face of the beam. Obviously when checking shear, we're going to check it at the ends, at the supports, and at regular intervals throughout. So you can find what the shear pattern looks like right through the beam, not just in one place. So over here is our shear diagram. So we can see that we've calculated our shear 3 meters from the face of the beam. There it is, 568 kilonewtons. And bear in mind, once again, like I said, that is an ultimate limit state. You see, we've factored. Okay, just bear that in mind. All right, let's move on to the next page. One of the things we need to discuss, we need to calculate here is the position of the ordinates on the parabola of the of the cable profile, the pre-stressed cable profile. So what I've done here, this is page 7 of our notes for lecture 5. It's just a basic formula or an expression of a parabola calculation. I went through this in class once again. It's quite straightforward. Just work through it yourself, and you'll see how we calculate a parabola. In this example, you can see here it's just our cable profile, 760 deep midspan. It's a 27 meter beam, so half of that is 13.5 meters, as you can see there. The profile is symmetrical, and by calculating this, we can calculate what our eccentricity is at our point of interest, like we've done there. Okay, so just work through that example, you'll be able to figure it out. Right, now this is quite straightforward. FT, for instance, there we go, quite straightforward. 0.23 times root FCU, that's easy. FCP, right, what we need to do here is calculate, as I said, we need to know what the bending stress is at the neutral axis, and it's due to just the pre-stress force only. Okay, so we've got our P upon A, PE upon Z. Now this P here has been expressed as a function of the losses at the 3 meter point, okay, a loss factor at the 3 meter point that will reduce our initial pre-stress at the end of the beam to give us an effective pre-stress at that point. Now, if in a test or an exam you're given an effective pre-stress, obviously we don't need to factor it any further. That is the effective pre-stress. So neta times P over here is the effective pre-stress, in other words. Okay, in this particular case, we're working to a neta factor there of 0.8, in other words, a 20% loss at 3 meters along. And that's how we're working this in this particular this particular example. In a test, I would possibly have given you a P effective at that point. Bear in mind, if I give you a P effective, you do not need to calculate any further losses. This is quite straightforward. One gets a normal stress diagram, and we calculate FCP at the neutral axis. This example, of course, is a symmetrical beam. So FCP is halfway up, very easy to calculate. I did put a little note here that if a beam is symmetrical, then we don't really need to calculate the whole formula. We just need to use P upon A. And that would have given us that form if it's symmetrical. If it's not symmetrical and Z top's not equal to Z bottom, then the full procedure would have to be followed. Okay, quite straightforward. Okay, now I'm going to go on to talk about the vertical component of the pre-stress force they're talking about. Now, in order to calculate the tangent at 3 meters in from the end, that is our point of interest. In order to calculate the tangent of the pre-stress force at that particular point, which we need so that we calculate that slope of the line, so that we can determine what the vertical pre-stress component is, we need to know what the equivalent radius is of an equivalent parabola. We did that, if you recall, we did that in lecture 3 when we were calculating losses. Lecture 3, page 8, we calculated RPS. We even reuse that same value, and we can, by following this simple little formula here, we can calculate what the slope of the tangent is at that point. In this instance, it's 5 degrees. In the vertical component, very straightforward here. We've got our effective pre-stress, in this case, neta times P, and we've got the sine of that 5 degrees. It'll give us the vertical component, and we have an upward force. In other words, it's assisting us in shear of 270 kilonewtons that we add on to our VCO calculation. Just a little aside note here, this works perfectly for a simply supported beam, as what we're dealing with at the moment. If we do a continuous beam and the cable profile wasn't a simple parabola like this, but a complex parabola going over the support, we would have an eccentricity that's above the neutral axis, and of course this would not assist our shear. It would in fact make our shear a little bit worse. We would have to take that into account. But in this example, as we're working only with a simply supported pre-stressed beam, I'm only going to continue and show you that you will add that on to assist your VCO. But bear in mind that if this was a continuous beam, then near the support, your pre-stress actually makes your shear a little bit worse. We need to then deduct it, not add it. But anyway, in this course, we're only dealing with simply supported, simplified, and so we're going to add it. So anyway, here we are, our VCO, shear resistance of the beam at 3 meters from the support, uncracked in flexure. We've got there 1,557 kilonewtons, quite straightforward. I just, those values that we calculated just now substituted into the formula, very easy. Okay, I'm going to go back now to talk about VCR and then skip back to the VCR example in the note. Okay, the section cracked in flexion. Now this is more than likely going to happen somewhere towards the middle of the beam, where in the ultimate limit state we have quite a high bending moment. Although the shear might be low, the bending moment might be high. We need to calculate a few clever little things here. VC, quite straightforward, we're used to that. We see that as for reinforced concrete. We need to calculate also MO, which over here we see as a decompression moment, as we call it, is the moment required to produce zero stress at the extreme tension fiber of the section, and it's always positive, and tension face is the face that would be in tension from the applied loads only. In other words, the dead loads and the live loads that are causing that tension, that's considered to be the tension face. We'll go through that MO in the example. Just something to look at here, this calculation for MO. I, the second moment area, YT is the distance from neutral axis to the tendon, that YT. So basically that is your eccentricity. Okay, FPT is the stress at level D due to pre-stress only, always positive. Okay, so FPT, we have to calculate that as well. Quite straightforward to do so, and it's just our simple equations to do that. We need to calculate also FPE. FPE is taken as usual, but no greater than 0.6 FPU. Okay, so that'll be your effective pre-stress force divided by the pre-stress area for FPE, but we'll go through that in an example. D is the distance from the compression face to the center of the pre-stressing steel. When this says steel area, I mean pre-stressing steel area that we have here. Okay. Note that there is a VCR min value of 0.1 BH times the square root of FCU. We'll discuss that a little later. Okay, let's go through the example. Okay, to continue with the example that we've got in our notes. At 3 meters, we're going to check the shear cracked in flexure now and compare that with the uncracked in flexure at that point. Okay, for this we need to know two things. Firstly, we need to know the moment at 3 meters, and that is the ultimate bending moment, and we need to know the shear at 3 meters, that is the ultimate limit state shear. So we need to know that. Right, FPT, the stress to pre-stress only, we can just the FPT, which we require for this MO calculation, as we discussed on the previous page, the stress due to the pre-stress only. Okay, firstly we need to know that eccentricity at 3 meters, we already calculated that for the VCO. We'd calculated that already, so that's our 300 millimeters. That is YT, so that's our eccentricity. Quite a straightforward calculation here if you just follow the formula that I've shown you. So we can get an MO that we need here. Quite straightforward. Once again, just follow the example and you'll be fine. FPE, here we go. We've got our effective pre-stress force divided by APS. Okay, 1106 MPa. Now if we look at 1106 MPa over the FPU, which is 1680, we've got an FPE over FPU of 0.65, which is greater than 0.6. So in that case, FPE has to be 0.6 FPU, 1008 MPa. So don't forget that. The maximum value of FPE is 0.6 of FPU. Okay, just a few little things we need to calculate here. D, obviously this is the depth from the compression face down to the pre-stressed steel. Quite a straightforward calculation. VC, this is exactly as per normal reinforced concrete. Okay, now we can build up our little formula for VCR. We've calculated everything we need. Put it all in. Just watch your signs. Watch your units as well. Calculate your VCR, in other words, your shear strength of the beam for the cracking moment. VCR, we need to compare VCR and VCO. So VCR is less than VCO. In that case, VCR governs. So VC is equal to VCR in this case. We need to do the comparison here to see what kind of reinforcement we need to put in here. Before we do that, let's go back to the notes. Okay, back to the notes here. Right, we need to have a look at different conditions under which we do apply reinforcement. Reinforcement can be omitted when our V is less than 0.5 VC. Otherwise, minimum reinforcement is supplied when VC is greater than V, and that is greater than 0.5 VC. There's our minimum reinforcing that we need to supply. Remember, B is not the flange width, it's the width of the web. When V is greater than VC, then shear reinforcement is required. Please also check that this doesn't become less than the minimum. But anyway, we can calculate here what shear we require. It's exactly the same as a normal shear calculation. You're going to calculate ASV over SV. So everything there is the same. You're familiar with that. What you need to just remember here is that dt that they refer to here is the greater of these two depths. So it's not to the center of the pre-stress, it's the center of the reinforcing around which the link covers. And then have a look at the bottom of this page here. Please read this minimum spacing of links. Make sure you get that right as well. Just read that through and make sure you understand that and apply it correctly. I'm going to pause again now. Okay, we're back to the example then on the last page. In this particular instance here where VCR governs, so VCR is VC. V is 568 kilonewtons. 0.5 VC is 497, which is less, so the minimum shear reinforcement is required. So minimum ASV, ASV of SV exactly as per our formula that we're given for minimum shear. In this instance, we do a first attempt using 2 legs of R8 mild steel rebar. We get the steel, the links spacings of 136 millimeters. This is quite close. So let's try 2 legs of Y10, ASV of SV, there we go, 0.4, our ASV is 157 millimeters, that's 2 legs of a Y10, so we're looking at 392, say 400 millimeter centers. I would have said Y10s at 400 would be sufficient. Just check also the minimum spacing requirements as we discussed. Okay, that's just a quick brush up on the shear that we covered in class. Work through it, work through the example, work through the textbook, and you should get it right.